Hello and welcome back to the channel. Ever wanted to build something really smart, like a search engine that understands what people mean, or a chatbot that can actually hold a conversation? You don't need paid APIs or credit cards to get started. Today, I'm showing you how to build AI-powered apps using completely free tools. Yes, even the vector database and embedding model. Think of this as the poor man's AI toolkit. We'll use the MongoDB Atlas free tier with built-in vector search and the Sentence Transformer library to generate text embeddings. This stack is super capable and perfect for building smart apps on a budget, or no budget at all. By the end of this video, you'll know how to set up a free MongoDB Atlas cluster with vector search, generate high-quality embeddings using sentence transformers, insert embeddings into your database, perform semantic search to find similar text, and you'll do it all without spending a single penny. Here's what you'll need: a free MongoDB Atlas account, Python installed with the Sentence Transformers and Pymongo libraries, and a Jupyter Notebook, which we're using because it's interactive, beginner-friendly, and lets you run code step by step while seeing the results in real time. Before we code, here's a quick look at what Sentence Transformers do. They take raw text and convert it into fixed-size vector embeddings, a format machines can use to understand semantic meaning. These embeddings let you do powerful stuff like search by meaning, cluster similar documents, build intelligent filters, and recommenders. So I'm using a Jupyter Notebook for this demo. So the first thing I need to do is to make sure that I have all my dependencies. So as you can see, I'm using Python, in which case I'll need to use the appropriate MongoDB drivers. So I'll install Pymongo and also make sure that I've got the Sentence Transformer libraries correctly installed. I did have an old version of NumPy on this machine, so I've had to upgrade it because I ran into issues earlier, so I'm running with this version here. So the usual, setting up the Mongo client, specifying my Mongo URI. Clearly, best practice is to make sure that these settings or that setting is stored in an environment variable .env file. For the purposes of this demo, I've just set it up here. The database that I'll be using is vector_demo, and I have my documents collection. I'll do a bit of tidy up since I'm running this for the first time. I'll do a bit of a tidy up since I've run this before. So first of all, I can run these blocks individually, which gives you an idea of what's happening at each step. So Jupyter Notebooks, great for trying to demonstrate concepts in a clear way. So let's first of all start with the dependencies. So set the dependencies up. I have set up my virtual Python environment and I am running that version of Python. So if you're going to be running any other version, you might want to update the dependencies, the versions of the Sentence Transformer, Hugging Face, as well as NumPy. Okay, so as it says here, these dependencies have already been configured. So next thing I do is to make sure that I can connect to the database. So I'll run that cell. And there is an error. So it tells me that the cluster that I'm trying to use doesn't exist. So I'll confirm the details of the cluster. So I'll go over into Atlas, and this is the cluster that I set up earlier. I just make sure that I have the right credentials. So I'll click on the cluster link, Looks like that might not be the cluster actually. So let me go back and instead I'll connect. So I need all of that. So I'll head back into Visual Studio Code and I get to update that part there. And I'll then plug in my very secure password. So that's done. Database access, edit, and then update my password. Edit the password, auto-generate, copy, and update the user. Back into Atlas, back into Visual Studio, and make the relevant update. So try that again. Okay, that looks about right. And the next thing is to set up the model and the method that does the embedding or generates the actual encodings. So obviously the caches needed to be warmed up. It's a much quicker response. And these are the documents that I'll be saving to the database. So what are these documents? These are meant to be movies. So a movie has a title, and a movie has what is essentially a plot. We're storing that in the variable in the field name text. So I will run this bit here, and I've just inserted these documents into my vector database. I can check to make sure that these documents are actually in the database. So I'll browse my collections, and let's look at a typical movie. So a movie in this case has a plot as well as the title of the movie and an embedding. That embedding is a vector that's got a length of 384 elements, as we can see there. We're not going to discuss quantization, which is an optimization technique that you can employ with very large vectors. That's probably something saved for the next video that I do. In this video, the focus is really just how to get you up and running using vector search. All the intricate detail for another video. You might also be wondering, if I had images, how do I handle images? How do I encode those? So clip enters the picture in that case, as well as some of the other embedding models. We won't be covering that in this video. In any case, let's head back. So these are the documents that I inserted. I can see the document identities coming back. That confirms the insert. So that's the setup of the data. The next stage here is where we actually create the index. So for the index itself, I have a variable that captures the index that we're creating. So these are the specifications of my index. The index is going to index the embedding field, and we're going to use cosine similarity in this case. If you remember vectors from back in the day when you're in school, we're told that vectors have both quantity and direction. So in this case, I'm only worried about the angle between the vectors. The smaller the angle between the vectors, the more similar that these two vectors are, i.e. the query vector and the vector on the embedded document. So in this case, we're only worried about the size of the angle between the query vector and the vector in the document in our database. The smaller that angle, the more similar these documents are. We're not worried about the magnitude of the vector. Hence, this idea of cosine similarity. How similar are these two documents? Okay, so this is what we've got. We create the search index. So MongoDB provides you with a way to actually create the search index from code, which is quite handy for this, because rather than doing that in the UI, you can actually see how it's done in code. So we'll create the search index. So the search index is now being created, okay? And the name of the search index is called default, and that's the type. That's a vector search index. If I head over to Atlas, I can actually see the index being created. So if I click on Atlas search, do a bit of a refresh, go there. So as you'll know, these are Lucene search indexes, but the great advantage here is that you don't have to pay any synchronization tax to keep your documents in sync with the actual index. So that's my index there, as you can see. So it says vector demo, that's the database, that's the collection, and we've created an index of type vector search on the embedding field. Okay, so that's what it looks like. The index is ready for us to use, and the index has been created on all 3 nodes that make up the replica set, as we can see there. So if you're new to MongoDB, you know that production deployment, minimum recommended production deployment is a 3-node replica set, primary with 2 secondary nodes. Okay, so I'll come out of here. My index is ready. Let's do some searching. So this is my query. I'd like to find a movie about travel and relationships. Imagine somebody typing that in the front end in the UI. We then have a method that actually does the embedding. So this method was defined much earlier, in case you forgot that. This is the bit here where we take some text in and we use the model that we've set up to actually generate the encoding. So let's see what that looks like. And I can keep track of my Jupyter variables, because that's a great way to see what's happened so far. So these are my Jupyter variables, and I can see what's been set up, when it's been set up, and so on. So anyway, that's our search index, which is the last step that we did. So for now, I will do a query, run a query, and I have a pipeline here. So the pipeline lists 2 stages. There's the vector search stage, and what that is doing is starting with 100 candidates in the top plane of my hierarchical navigable small world. So start with 100 candidates, i.e. 100 random vectors, and narrow the result down to 3. There's a projection, and in this projection we're also including relevance information. So I'd like to see just how relevant the results are. That's a very important aspect of search. Just how relevant are these results based on what the user entered. And a lot of re-ranking work will happen in this stage here. It could be the case that the behavior of my search doesn't quite meet the mark. So there's additional work we can do to make sure that we get exactly the correct behavior. Anyway, let's run the thing. And we get the results there. So it tells us that here is a movie with a plot that talks about an immigrant leaving his sweetheart in Italy to find a better place across the sea in the grimy slums of New York, blah, blah, blah. And then there's another movie here. A greedy tycoon decides on a whim to corner the world market in wheat. And if we look further in, it talks about poverty and so on and so forth. And then the next one is, at 10 years old, Owen becomes a ragged orphan, sainted mother dies, and so on and so forth. Now let's try something slightly different. I will take this bit of content I'll then go and try to translate it. So I will come back here and we'll say translate.google.com. And let's say that it's in English, but I'd like to translate it to, what language can that be? Yeah, we'll go with Lithuanian. So I'll copy that. And I will then go, in fact, better yet, let's do something like this. A romantic movie about a couple separated by distance. Okay, that's my version of that movie in Lithuanian. So I'll come back in here and plug that in. What are we going to get? So I'll run this, and it gives us the same result with obviously a very different score. Let's try something else. I'll take that out and we'll just say a film about a greedy businessman. So I will move this down here. At least we can see the scores. Run it. Okay. And then let's plug this back in. So such is the power of these tools. So clearly it's able to infer meaning from that bit of Lithuanian text without me having to spend an inordinate amount of time trying to translate stuff. Try that with different languages when you actually play with it. It's quite a useful feature. So that is really our demo there. So if you'd like to run this through, a few things that you'll need, obviously, the dependencies that I had up there, and got to install those, great. And if you'd like to do some background reading about some of the things that we've used here, the Python packages, the sentence transformers, this is where you'll find more information. So it's SBERT, that one there, sentence transformer documentation, and you can get to see how to work with it. So all I've done here is really scratch the surface, but hopefully it shows us that you can actually build this class of application without having to spend a fortune in API keys, GPUs. There will be some compromises, clearly, but that's like any engineering solution. So clearly there are things that we're missing from taking this approach. Drop us a like, subscribe, share. Okay, until next time, thank you very much and take care of yourselves. Bye now.